Okay, good afternoon, class. I hope all of you have submitted the tutorial as it was due, I think, at around 1 p.m. today, right? So you needed to submit the tutorial in order to get the 1%. I think tutorial is allocated 10% altogether, right? So I'm not sure whether one tutorial is equal to 1% or how it is going to be divided at the moment, but it will be roughly around 1%, right? So let's start with this week's tutorial. There's 4 questions that has been given altogether, right? So um, I hope all of you can see my screen, right? Okay, all of you can see my screen? Yes, I can see.
Yes, sir.
Okay, great. So question number one was to find V out upon Vs, assuming ideal op-amp, right? So basically, we needed to, we just need to find the gain of this particular circuit, right? You can use the direct direct formula that the direct formula for finding the gain of a non-inverting amplifier, right? That is 1 plus RF upon RI, right? Or 1 plus R1 upon R2, right? So in this particular case, it will be 160 divided by 40 plus 1. So you should get a gain of 5, right? But in this particular case, we'll use the circuit analysis, right, that you have learned in E102 to compute the gain of this particular circuit over here, right? So if I mean this, if we draw the current flow in this particular circuit, right, it will be in these particular directions, isn't it? And then what we can do is we can label these nodes, right? This node over here and this node over here, right? So if we write the current, the nodal equation for this particular circuit, over here we know that V2 is equal to Vs, right? That's simple, right? And from these, if we write the nodal equation for this, right, for the node voltage over here, if we write the equation for this, it will be V naught minus V1 divided by 160, right? V naught minus V1 divided by 160, which is equal to, because the same current is flowing over here, right? There is no current that will be flowing over here, right? Okay, because this is a feedback system, so the gain is basically defined by the feedback system, not by the op-amp itself, right? So there is no current flowing into the op-amp, right? So the current will be just flowing in this particular direction indirectly through this resistor and downwards, right? So basically the current equation over here is V0 minus V1 divided by 160, which is equal to V1 minus 0 divided by 40, right? So this is the equation that we get, right? Now, since we know that the in a feedback amplifier, what happens is that the gain is basically defined by the feedback itself, right? Not by the op-amp. So what that indicates is that the total, the total voltage difference across the positive and the negative terminal will be 0, isn't it? So that means that voltage at V2 should be equal to voltage at V1 in order for the op-amp to result into a 0 gain, isn't it? Right? So the gain won't be defined by the op-amp itself, right? So in that particular case, V2 will be equal to V1, right? And we know that V2 is basically equal to Vs, right? So V1 is equal to V2, which is equal to Vs, right? Now substituting these into this particular equation, right? So basically substituting V1 with Vs, we get this particular equation over here, right? So, so we have a resulting equation of this. Then what we can do is we can make V naught upon Vs the subject of the formula in order to find the gain. So if we solve for this, we'll be getting V naught upon Vs is equal to 5. Okay. Anyone has any questions regarding this circuit over here? All of you are okay with this? Okay, let's move on to question number 2, right? Okay, someone just asked, how do we know that V1 is equal to V2? So all of you know that in a feedback amplifier, the gain is not governed by the op amp. It is the feedback that defines the gain of the system. So we don't want any resultant gain from the op amp. Okay. So in order for the op amp to give is to have no input into this input signal, I mean, in order for the op amp not to have any input in the gain, V1 has to equal to V2. Okay. So the resultant going into this particular op amp should be 0 volts, isn't it? If the resultant is 0, the output of the op amp will be nothing, right? Isn't it? So that is why V1 is equal to V2, right? If the difference voltage is 0, or the op amp is basically operating in common mode, so the difference will be, I mean, the gain of that op amp will be, I mean, the op amp won't be contributing any gain towards the overall circuit gain, right? So that is why V1 has to be equal to V2, right? I hope that you are clear with that, right? So that is why V1 is equal to V2, so that the op amp does not make any sort of contribution. Okay. Okay. Question number 2. Find V0 upon Vs. Again, find the gain assuming the ideal op amp, right? So if the op amp is ideal, so what happens again? Like I said, in order for the, I mean, since we have a feedback system over here, right? So basically what that means is that the gain is basically controlled by the resistors, isn't it? Or the feedback system, not by the op amp. So what happens is whatever voltage we have in this particular branch, or whatever voltage that is going into this particular terminal, should be equal to the same voltage at this particular terminal as well, right? So in this particular case, the voltage going into the positive end is 0. So the voltage at the negative end should be 0 as well, right? The differential voltage across this op amp is 0. Okay. So there's if this is grounded, what happens to this particular part? It is virtually grounded, or the voltage at, if the voltage at this particular node is 0, we create a virtual ground, isn't it? Right. So that is where we get the virtual ground from. Okay. Okay. That is why we say in a inverting amplifier we have a virtual ground. All right. Now we need to find V0 upon Vs. So basically it's a gain of the circuit. So you can use the direct formula that you have based on the resistor ratio, right? That is, the gain of this circuit is basically equal to 160 kilo ohms divided by 40 kilo ohms, right? So basically the gain of this particular circuit is 4. So we know that through the formula, right, itself. But how do we go about doing the analysis of this circuit, right? So if you pay close attention to this particular circuit, you'll see that there is no current flowing in this particular branch. That is fine. So in this particular branch, whatever current we have, it will flow in this particular direction. Since this particular node is virtually grounded over here, so whatever current we have that flows through over here, it just directly flows to this resistor as well. Okay. So the direction of flow of the current is somewhat like this, right? Okay. So again, performing the nodal analysis on this particular case, right? So we know whatever current is equal to whatever current is flowing in this branch is equal to whatever current is flowing in this particular branch. So the current of this particular branch is basically given by Vs minus 0, right? This is virtually grounded. This particular node over here is virtually grounded. So Vs minus 0 divided by 40, right? Vs minus 0 divided by 40k, right? Right? Vs divided by 40k, right? And the current flowing in this particular branch will be 0, right? This node over here has 0 voltage, so 0 minus V out. So we have negative V0 divided by 160, right? So this is the equation we get by performing the nodal analysis at this particular point, okay? So now we have the equation in terms of V0 and Vs. So we can make V0 upon Vs the subject of the formula. So if we make Vs upon V0 the subject of the formula, we get the gain as 4, minus 4, right? So that's how we get the gain of this particular second is -4. Okay. Let's move on to question number 3. The third question of this tutorial. Find V naught in the
V naught in the following circuit, assume an RL of M.
Yep. Okay, anyways. So so again in this particular circuit, we can see that okay. Again, in this particular case, we need to analyze this particular circuit over here, right? Okay. So in order to analyze this circuit, again, what happens is that we can just make a nodal analysis, right? So you can see this particular branch is already grounded. So there is no current flowing into this particular in this particular terminal, isn't it? So we can just directly perform the nodal analysis of this particular, of this particular nodal, what do you say? Sorry, the nodal analysis for the negative side of this op-amp, right? Okay, this particular. So if we draw the current direction, remember, like I said, there won't be any current flowing into this particular op-amp, right? We don't want any contribution of the op-amp, right? I mean, no voltage amplification due to the op-amp itself, right? So basically, there won't be any current that will be flowing into this op-amp, right? So in that particular case, right, we just have one node, right? This particular node is just basically 0, right, or virtually grounded, because this, like I said, if the bottom node is already grounded, so what happens to the top node? This particular end has to be grounded as well, right? There's no node, but virtually this particular terminal is grounded, right? Okay. So what happens is, if we perform the nodal analysis, we only have this node over here, that is Vx, and if we draw the current direction in this particular circuit, it will be something.
Hello, bhai.
Yeah.
Hello.
Please try to mute.
Hi.
Wait, just hold on. Let me mute everyone. Okay. Right. So drawing the current flow in this particular circuit. So let's assume that the current is basically flowing from this end, right? Okay. So current is being flowing in this particular end, right? So if current flows in this particular direction, there is no current going to be flowing in this particular branch over here. So whatever current we have in this particular branch will flow directly down, right? So writing the equation at Vx, right, at this particular node. So we have, just by observing, right, whatever voltage is across this particular node, we can say that this particular node forms a supernode, right, over here. This is a supernode, right, basically. So whatever voltage we have at this, across this particular branch is the same voltage at this particular point as well, isn't it? So basically Vx is equal to 2 volt, right? This particular end is already 0. So this 2 volt should be reflected at Vx, isn't it? So Vx is basically equal to 2 volt, right? So now writing the equation of this particular node over here, we know that, if we write the nodal equation at Vx, that would be V naught, right? V naught minus just excuse me for a bit. Okay, you can directly, this particular part over here is just in terms of some other format. It has been given in terms of mesh analysis, right? But you can write it in terms of nodal equation. So that would be V naught, right? That is V naught minus Vx divided by 20 kilo ohms is basically going to give me I, okay? And Vx divided by 10 is going to give me I, right? So that is what we have. I is basically equal to Vx, right? For this particular branch, we have Vx divided by 10, right? Vx divided by 10 is going to give me I. Okay, so the current flowing in this particular branch is basically equal to 0.2 milliamps, right? It is basically, in this particular case, the calculation given over here is just direct evaluation and substituting but you can also write the nodal equation as well, right? It's the same thing, like I said, right? So the current flowing in this particular branch is basically 0.2 milliamps, right? So what that means is that this is the same current that is going to be flowing across this particular branch as well, right? And we just need to find V0, right? Isn't it? So what happens is that now if the current is flowing in this particular direction, so it is V0 minus, right? V0 minus, if you do the mesh analysis in this particular loop, so V0 minus I times 20 kilo ohms is going to give me Vx, isn't it? So V0 minus I times 20 is going to give me Vx. So Vx is 2 volt, right? Like we have already mentioned over here. Solving for V0 is going to give me 6 volt. Okay. Anyone has any questions regarding this one? Anyone has any questions regarding this particular question? Your mic must be switched off. Okay. So remember again, I'm just going to repeat this again, that you just need to perform your nodal analysis over here, right? Just as at this particular point, right? Because the voltage difference, there shouldn't be any voltage difference that should be going across this op-amp, right? So basically this particular point, just after this negative terminal of this particular battery is basically grounded, right? Okay. Or there's 0 volt that is being going into this particular negative terminal of this operational amplifier. So that is why we just have directly 2 volt being supplied at Vx, right? Okay. And you can directly solve this if we know that. So if Vx is basically equal to 2 volt, right? You can just directly perform your nodal analysis and you'll be able to solve for V0, right? Because you will be easily able to solve for I, and then using the nodal equations, you can solve for V0, right? In this particular case, the first thing was done that the current I was calculated for this particular branch, and then using the mesh analysis for this particular branch, V0 was calculated, right? Question number 4, design an inverting op-amp circuit for which the gain is -5 volt per volt, right? Or just the gain is -5 and the total resistance used is 120 kilo ohms, right? So V0, so basically what this means, if the gain is -5, right? So what this means is that V out upon Vi is basically equal to -5, isn't it? And the gain of an inverting amplifier is given by -R2 upon R1, isn't it? So based on this equation, we can solve for R2, right? So R2 is basically equal to 5R1, right? Keeping that in mind, right? This becomes our equation 1. Then we know that the total resistance used in this particular circuit is 120 kilo ohms. So basically what this means is R1 plus R2 is equal to 120 kilo ohms, right? So that forms my equation number 2, right? R1 plus R2 is equal to 120 kilo ohms, right? Then you can either use elimination method or substitution technique, whatever method you want to use to solve this simultaneous equation, right? Since we have 2 variables and we have 2 equations, we can use our simultaneous equation technique to solve for our R1 and R2. We have 2 unknowns and 2 equations. So it is solvable. You can solve this, right? So using our simultaneous equation, if we solve for R1 and R2, we should end up with R1 is equal to 20 kilo ohms and R2 is equal to 100 kilo ohms, right? So remember, once we have found our R1 and R2, that doesn't end here because it says design and inverting op-amp circuit, right? So we need to draw the op-amp circuit as well, because this particular statement over here, or this particular line over here indicates this one, the highlighted part indicates that we need to draw the circuit, right? We need to design the circuit. So you just need to draw the circuit something like this and make sure that your R1 value is 20 kilo ohms and your R2 value is 100 kilo ohms, right? So this is the full solution for this particular question. It doesn't end at just R1 is equal to 20 kilo ohms and R2 is basically equal to 100 kilo ohms, right? So you need to draw the circuit as well. So with that, our tutorial comes to an end, right? So anyone has any specific question regarding this week's tutorial? I'll give this time for you guys to discuss anything that you want to discuss, right? If you don't, then we'll end this session over here, right? It's totally up to you. You can turn your mic if you want to speak up. You can turn your, you can unmute yourself, right? So all of you are okay with op-amp circuits, right? With operational amplifiers.
Yes, sir.
Okay, great. So we'll end this session over here. For next week's session, please again try to complete the tutorial task, the tutorial submission just before time, right? Not like today. I think most of the students submitted last minute, right? So try to submit it before, and see you next week, right? Set. So I'll end the session over here. Thank you for joining.
Thank you, sir. Have a good day.